So this video is going to look at problem solving with forces for learning target 3.3, and there's a few example problems we're going to work through that are on homework assignments that will hopefully help you see how these should be done. First, it'd be important to remind you of the problem solving steps. First, we're going to draw the free body diagram. We always label the forces acting on the object. Then we would write the expressions for Newton's second law. These are what I call the F net equals ma expressions. We'll look at the x and the y direction separately so that we can get the full picture of what's going on. Once you have your F net equals ma expression, it's always filled in here on this blank based on what you had in your free body diagram. So for example, with the lab that we did, that we had the force sensor upwards, we called that a tension force upward, and the force of gravity downward. Then my expression for how I would find the net force there, it would just be a subtraction. Oops, but that is x. This is y direction. So I would say force of tension minus the force of gravity gives me my mass times acceleration. There is no net force in the x, and there's no forces acting. So for the simple little demo here, tension minus force of gravity equals ma, and then I can go charging away using this as my primary equation to be solving that problem. It helps if I can put other expressions into that when I do step 3, substitute in any other values. So for example, Fg, the weight equation, equals mass times gravity. So I can substitute that in to that expression too. That's another option. And then this should say step 4, I would be solving for the unknown. Let's take a look first at workbook, page 113, number 2. I had said to use g equals 9.8 for this one because of some of the planned values on there. So we're going to remember that. A 5 kilogram box is at rest on a surface, and the coefficient of static friction and kinetic friction are 0.5 and 0.33. So this is the coefficient of static friction and the coefficient of kinetic friction. Determine the force of kinetic friction that would act on the box if it were in motion. So this is just a simple level 1 substitute and solve. My force of kinetic friction is mu times the normal force. Okay, what's the normal force? Well, I should draw a little picture to remind myself. If this is hopefully on a horizontal surface, that was my intention at least. Makes it a little bit simpler. I've got gravity down, normal force up. If the box is in motion, maybe I'm pulling it, or maybe it's sliding already. Either way, there's my force of friction. I'm looking for just knowing what that force is. So that's my coefficient times normal force. What's the normal force in this situation? Well, here, since the net force in the y direction is 0, then I know that my up force equals my down force. So in other words, my normal force equals the weight of the object. Substituting that in, I would take my coefficient of kinetic friction is 0.33, and my normal force, which is Fg or mg, and I would substitute that in as well. So mass of 5 times an acceleration of gravity of, we're going to use 9.8 here. That gives me a force of friction, kinetic, equal to 16.17 newtons, or around 16.2. So that's my force right here, if I'm in motion. If the box is already moving, what is the acceleration if you push it with each of these forces? Well, that's when I would be looking at taking my force diagram here and know that I'm pushing it or giving an applied force. So we're going to test out these different applied forces. And we're going to say my net force in the x direction equals ma. And I'm solving for a. So for the net force in the x direction, I would be finding that looking back at my force diagram by saying I've got two horizontal x forces. my force applied and my force of friction. I would just be subtracting those two forces to get the net force. So force applied minus force of friction equals MA. And again, I take this side of the expression in order to continue working the problem. My applied force for the first situation would be 20. And my force of friction is always going to be that 16.2 equals MA. My mass is 5 times the acceleration. So 20 minus 16.2 is 3.8 equals 5 times A. Divide that out, and I get an acceleration of 0.76 for that first scenario. If I look at the scenario II, it's a applied force of 16.2. Then I'm going to take that as my applied force minus my friction force equals MA. The left side becomes 0. So therefore, the acceleration must be 0, and that would mean that the object is moving with a constant velocity. That's why we chose 9.8 instead of 10. The third scenario of a applied force of 10, now I have 10 minus 16.2 equals 5A, and that's going to leave me with a net force of negative 6.2. So that means if it's moving to the right, but I'm not pushing it hard enough, it's actually going to slow down. So when you take that negative 6.2 divided by 5, I get an acceleration of negative 1.24 meters per second squared. So if I'm only pushing with 10 newtons and friction is bigger than that, it's very quickly going to be slowing down and stopping. Continuing on with this problem, part C is looking at determining the maximum static friction force. Remember, the force of static friction actually is an inequality. It's because there's a threshold value, but friction will also match whatever it needs to be if it's in the static situation if you don't have enough to exceed that. We talked about this in class notes. As a reminder here, though, when we're looking for the maximum, we're looking for that threshold value. So that's where this expression becomes the equals sign. Okay, so that's force of friction, static. The maximum is when it equals mu SFN. Okay, so that maximum static friction force, that's this side of the equation. Okay, so we're going to solve that by looking at, remembering that this 0.5 is our mu S, and our normal force, like it was before, if we have the same force diagram, force applied, our normal force just balances the weight. Okay, and so that's going to be m times g, which is 5 times 9.8, and then times that 0.5 for the coefficient. Comes out to be 24.5 newtons. So that's the biggest that static friction force could be. So if I push, if I don't push with enough force, then friction can continue to oppose me up to the point of 24.5 newtons. So let's take a look at part D. If the box is at rest, so static friction conditions, what happens if you push it with 24.5 newtons? So if I can have a maximum static friction force of 24.5 newtons, and I push with 24.5 newtons, that would seem like we have a net force that's 0, right? Because if you are taking your horizontal forces, force applied minus the force of friction, that equals MA, it would seem like this has 0 for the case of 24.5. Let me write that over here. So 24.5 applied minus 24.5 maximum equals MA. So we would think that that should be 0. But the way that it is with friction is that if you push just a little bit more than 24.5, then the object will start to move. So the thing is, you only have to push a little bit more. So that might be 0.0000000000000000001 newtons more than 24.5, that threshold, which for all purposes is basically still 24.5. So if you push equal to the maximum static friction force, it's going to start moving. So we would say, because this is at the threshold, so it just starts to move. Okay. In the case of pushing with only 20 newtons, okay, with 20 newtons applied force, and friction is able to push up to 24.5, it's not going to move, because you have to push over that threshold value of 24.5 newtons for it to start moving. So if you push, if F applied is equal to 20 newtons, then not enough to overcome, there needs to be a C in there, to overcome the force of friction static threshold. So no motion. The object's going to stay at rest. Now here's the thing that sometimes throws people. If you are applying a force of 20 newtons and there's no motion, that means that friction is also 20 newtons. So the force of friction is 20 newtons in that scenario, so that you have balanced forces, even though it can push up to 24.5. If you only push with 20, friction only pushes with 20. Okay? If you push with more than 24.5 newtons, this last situation of 30 newtons, you're going to have 5.5 newtons beyond the threshold, and that's going to make it start to not just barely start to move, it's going to definitely accelerate. Okay? And so if it's going to accelerate, you'd have that net force of 5.5 equal to ma, and you could solve that for acceleration. Taking a look at the next page, Workbook 114, number 2. Now this one is not assigned on homework for a couple of days after the friction one, but if you're ready to use this one as a good example, just to review, now's as good a time as any. The cable supporting a 1650 kilogram elevator has a max strength of 25,500 newtons. What's the maximum upward acceleration it can give the elevator? So if we're talking about max strength, that would be a biggest up force. So that would dictate a biggest or maximum acceleration. We're going to start this problem with drawing our force diagram. So we've got an upward force of tension and a down force of gravity. I'm drawing the force of tension upward because we're talking about an upward acceleration, so that would require a net force upward, so we need to have a bigger upward force. So we can start taking a look at what we know here, our force of tension. The maximum threshold value that we're looking at is 25,500 newtons. Our force of gravity is mg, and we know the mass is 1650 kilograms. And I'm feeling like using 10 today. So I'm going to use G equals 10 on this one. So that gives me 16,500 newtons for my downward force. Okay. What's the maximum upward acceleration? Again, we're going to push ourselves to make sure that we are writing our expression. F net, in this case in the y direction, equals ma. And I'll fill this blank in with the forces as variables. Now we can start to put in our numbers. We know 25,500 minus 16,500 equals the mass times acceleration. This becomes 9,000 equals 1650A. And then divide that by both sides by 1650. And my acceleration comes out to be 5.45 meters per second squared. That's my maximum acceleration upward. Looking at this problem, we have a 110 gram hockey puck sliding on the ice for 15 meters before it stops. We're going to be looking for the magnitude of the friction force and then also the coefficient of friction. When I see this in grams, I know I should be converting that, which there's 1,000 grams in a kilogram, so that leaves me with 0.110 kilograms as my mass. We should start with drawing our force diagram. And we've got a force of gravity downward and the normal force upward. And if this object is sliding, let's say to the right, that would mean that friction is to the left. And we don't have any other forces acting. If we have, if we're trying to find the force of friction, we know that we have the equation for the force of friction kinetic equal to mu times the normal force. Now, using this force diagram, I could see that the net force in the y direction is 0, so that tells me F normal equals Fg. So I could find the normal force to find the force of friction, but I don't know the coefficient of friction. That's what part B is asking, so I can't use this equation just yet. I'm going to have to use my force diagram and think about how to get to finding the friction that way. So we know that if you have an unbalanced force to the left, it's going to be causing the mass to accelerate. So our negative force of friction, negative because it's in the negative backwards direction, is going to equal mass times acceleration. So if I can use that expression, I can find the force of friction. So I need to know the mass. I got it. I need to know acceleration. I need to use a motion equation to find that. So let's take a quick minute and do that. Your initial velocity is 6, your final velocity is 0 because you're stopping, and then your displacement along the ice is 15 meters. So the equation that we need to use is Vf squared equals Vi squared plus 2 times A times the displacement. Substituting some numbers in, we get 0 equals 36 plus 30a, and then acceleration with some rearranging comes out to be negative 1.2 meters per second squared. So we can use that in our expression here to find the force of friction. So I'm going to label this as part A. So our negative force of friction is going to be our mass, 0.11, times our negative acceleration, negative 1.2. That comes out to be 0.132 newtons for my force of friction. That's good. It's kind of small, but that's because our hockey puck is not super big. Then we can use our friction equation to find the coefficient, now that we know the other pieces. Our force of friction is going to be 0.132. We're looking for the coefficient mu, and the normal force is equal to the weight. We already knew that, so I'm going to go ahead and substitute that in as m times g, because Fg equals m times g. So our mass is going to be 0.11, and gravity I'll use 10. And so in solving this one, you get a coefficient of friction of 0.12. That has no units because it's a ratio of newtons to newtons. So that would be that problem. It was interesting we had to use the motion equation again. And last problem I think we're going to do is this 114 number 4. We are using a horizontal force to push a block against a vertical wall. So the wall is like this. It'd be nice if that were a vertical wall, a little more vertical. And we've got a horizontal force pushing it against the wall. So that's our 7 newtons. And the block weighs 5 newtons, so that's our down force here, force of gravity. The coefficient of static friction is 0.6 and kinetic friction is 0.4. Will the block move? Well, this is only a couple of our forces, right? So you've got the applied force is 7 newtons, force of gravity is down, normal force is here. But normal force is perpendicular to the surface. The surface is vertical, so our normal force is actually this way. It's a little tricky. What is our normal force? Well, it's probably not going to be doing anything horizontally, accelerating in the x. So we can say the net force in the x direction would be 0. So that tells me that the normal force is balancing the applied force. So that also equals 7 newtons. If this block is not going to be moving, it's due to a horizontal force that's parallel to the surface, and that's always friction, right? So if you push hard enough, then you get a big enough normal force so that your friction force, which is dependent on the normal force, gets big enough to hold it there, okay? So now looking vertically, the net force in the y direction, we've got a up force of friction minus the down force of gravity, and we want to know what's going to happen. So let's take a look at calculating what our force of friction is, if it's the static case, for example, and see how much static friction we have. So let's find the threshold value, USFN. How big can static friction be? If we have static friction is a coefficient of 0.6, and my normal force we already said was 7, so what's 0.6 times 7? That's 4.2. Okay, so we have a down force of gravity of 5, which is bigger than the maximum static friction threshold value. So this block is going to move because my down force exceeds the maximum that friction could pull back with. So if we say 4.2 minus 5 newtons equals m times a, I can find the initial acceleration of the block and start in on part B. So this is going to be negative 0.8 equals a mass. What's the mass of this object? We know the weight. Do we know the mass? Of course we do. Remember we have our, maybe I'll put it down here. Our Fg equals mg. We know 5 newtons is my force of gravity. Mass times 10. The mass here is just a half a kilogram. Okay, so 0.5 for my mass. And what's that initial acceleration? This is right when it's starting to move. It's going to have a downward acceleration initially, just due to the forces that we've diagrammed of 1.6, again negative because it's downward, meters per second squared. Okay, and that would help us with calculating, that's the calculated acceleration of the block. Again, to know if it moves, we need to know if the down force exceeds the maximum threshold value. And this side of the static friction equation is the threshold value that we're thinking about here. So I think this is the last slide. It's the last slide. I hope that this was helpful, and have a wonderful day.